The photoelectric effect was Albert Einstein's contribution to the logic chain that led to quantum physics. He used the photoelectric effect to support the quantized energy concept that Planck had proposed to describe the energy of radiation in a black body. The experiment uses a phototube. Light is directed to a metal surface, liberating electrons into the vacuum. The phototube is similar to a cathode ray tube, but the electrons are liberated with ultraviolet light instead of a heated filament. A CRT has very high voltage, so electrons travel through the field directly to the anode in a straight line. The phototube has low to no voltage, and electrons form a gas. They gradually make their way to the anode for evacuation. The experimenter controls light frequency and intensity. He also has an external voltage supply. Externally applied voltage does two things. It provides a reverse field repelling electrons away from the anode and back into the tube. It boosts or limits the number of free electrons on either side of the tube. Only the first argument was incorporated into the accepted scientific explanation, which will be outlined shortly. Modern experimenters use a photodiode or a photocell. The photocell is limited in value because the manufacturer provides the cathode material. This reduces the utility for atomic analysis. The modern experiment uses a current amplifier. The amp allows a much more accurate estimation of microcurrents than was available 100 years ago in the original experiment. Here are 3 graphs generated using the phototube. Experimental simulations are available on the internet, allowing you to follow the data acquisition. All graphs use sodium metal. Graph 1 shows the basic dataset acquired, using a manual voltage sweep for any frequency and intensity level. Graph 2 shows the light intensity affecting the current. Graph 3 shows that the current flow starts at the same voltage regardless of light intensity. Most graphs have long linear portions with curved ends near a stability level. Graph 4 shows a family of curves with different frequencies. The furthest curve to the right, at 550 terahertz, is the lowest frequency that produces current. This is the frequency cutoff for sodium. Graph 5 is derived from graph 4 and shows the cutoff frequency at point A, where the current ceases to flow. The other 0 current points are in a linear pattern. Figure 3 shows graph 5 expanded with different metals. Here is where the explanations were made, driving the theory. The goal was to transform the voltage curves into energy curves. The idea was that a radiated atom releases an electron with enough velocity to travel through the vacuum to the anode, countering the reverse field applied by the experimenter. The initial kinetic energy was, therefore, equivalent to electric field energy. The final kinetic energy after the electron traversed the field was 0 right at the anode. Since different metals had different voltage current curves, each was assigned a work function, W, representing liberation energy. The slope of the curve was assigned by Einstein as the Planck constant, importing the explanation of frequency energy from the blackbody experiment. Of course, in the blackbody, the mathematical model was formed for nuclear charge oscillating radiation versus electron liberation in the photoelectric effect. There are some problems with the explanation. They can be separated into knee, gas, and slope arguments. First, the knee. The stopping voltage assignment depends where, on the knee, the threshold is determined. Second, the gas. The probability that an electron released through ionization is directly aimed at the anode is very low. Finally, the slope. The work function was designed to deliver an energy value to the y-axis, substituting for the experimenter-determined stopping voltage. We will go through these arguments with some visual detail. Knee argument. The cutoff voltage assessment is arbitrary based on the experimental metering and threshold detection. The voltage curve goes nonlinear in the most important region. The experimenter has considerable latitude in setting the data point. This can alter the stopping voltage and the corresponding work function assessment. Gas argument. It takes millions of electrons to register on the meter. All these electrons are in a gas in the vacuum. The probability that an electron would make a clean run through the tube to the anode is small. The number of electrons crossing the anode is 100,000 per second for even the smallest registration on a modern, widely available lab meter. The accuracy available over 100 years ago was far less. Slope argument. Einstein assigned the Planck constant to the slope. An examination of the logic of this proposition begins with published values of ionization energies. This data was not available to him. Ionization energies do not align with work function-based electron liberation energies. Therefore, the work function is not a material property. It is only an artifact of the maximum kinetic energy assessment and the slope assumption. The work function and the ionization energy for sodium show competing slope assessments. This slide shows the transformation of the voltage frequency graph to the energy frequency graph. The work function is derived from the stopping voltage via the maximum kinetic energy assumption, designated Ke max. As stated earlier, the slope was assumed to be h, Planck's constant. A more meaningful slope based on experimentally determined ionization energy is much steeper. With the help of the modern orbital atom model, the ionization principle can be examined. Ionization requires coherent light to accelerate the easiest to remove valence electron on both sides of its orbit. Alignment of different atoms in a mini-atom sample allows slightly different frequencies to excite different atoms based on their orientation to the incoming light. This slide shows 3 different orientations of atoms in a solid. A different frequency is required to accelerate an orbiting electron on both sides of its orbit, leading to elliptical alteration and ultimate ionization. Some frequencies excite the electron by reinforcing the Lorentz force acceleration, ultimately leading to ejection. Other frequencies work against each other, alternately accelerating and decelerating an electron, preventing ejection. Valence electron radii for ρ1 and ρ2 periodic table elements are slightly lower than that of hydrogen at 0.084 nanometers. From the analysis of ρ1 and ρ2 elements, it can be inferred that all atoms have similar valence electron radii and therefore sizes. Hydrogen's 0.084 nanometer radius corresponds to a light wavelength of 91.175 nanometers. This is the faintest, and therefore the stability point, sometimes designated the infinity wavelength, of the Lyman series. 90 nanometers is used in this example as a typical shortest wavelength to induce the departure of valence electrons from their orbit. There's an alternating pattern in the excitation curve between 0 and full power delivery to change the orbit of an electron. Higher frequencies allow faster excitation. This graph is an estimate showing the effect. Some frequencies excite an orbiting electron while others cause no effect due to alternating radiation fronts working against each other. This supports the idea that transmitted power is directly proportional to the frequency. as identified in the Planck relation. Ultimately, Einstein's analysis of the photoelectric effect was a logical loop with variables on each side of the equation, designed to open up quantization to the energy sphere via light transmission. Extraordinary assumptions were made in the photoelectric effect, which led to the definition of an energy packet based solely on the frequency of light. Einstein co-opted Planck's epsilon equals HF formula for a radiator element and turned it into capital E equals HF, defining a minimum unit of energy transfer, later named a photon. The tweaked formula was subsequently labeled the Planck-Einstein relation. This idea laid the groundwork for the Bohr atomic description.